Hey, what up guys? Welcome back to my blockchain channel, and today we're going to talk about how you can compare a hash to a normal number. So if you have watched my video on what a Bitcoin block consists of, you know that in order to mine a block, the miner needs to guess a nonce and then append the nonce to a hash of all of the transactions in that block. So we take all of the transactions in the block, the hash of those, we append the nonce to this hash, and then we hash this string, and we get another hash. And so this hash that we get when we hash the nonce together with all of the transactions, the hash of all of the transactions, when we hash these two together and we get a new hash, so this hash needs to be lower than the target. And the target is the difficulty. So the lower the hash, the harder it is to get such a hash. So the lower the difficulty, the harder it is for a miner to get a hash that is below that difficulty and to mine the block. And so you guys have asked me, how can you compare a hash, which is a string of numbers and letters, to a regular number, which is the target difficulty number in a block? And this is exactly what we're going to talk about today. And in order to do that, you guys need to come closer here and we'll look at some examples. Right, guys? So let's get into it, guys. Let's look at the first red number we have here. So this looks like a hash, and all of the hashes look approximately like this. We have 0, X, and then some letters and some numbers. Usually the hashes are a lot... let me get some light. So usually the hashes are a lot longer than this. Maybe they are 10 times as long or something like that. But this is just a short example. We have 0x. This is how all of the hashes start. And then we have some numbers and letters in a combination. And so how can you compare this to a number like 10, for instance? How do you actually compare this to a normal number? Well, first of all, we need to understand that this is in fact a number. And the only difference between this number and a normal number is that this number is written in the base 16 representation. So, as you know, guys, we use numbers from 0 to 9, or we use digits from 0 to 9, meaning that in the regular number system, we are operating in the base 10 because we have 10 digits. We have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 10 different digits. However, in base 16, we have 16 different digits. So if you convert this number to a number in base 10, you'll get this number. So this number in base 16 is equals this number in base 10. And this is called the hexadecimal notation, meaning that the number is in base 16. And this is the decimal notation, and that is in base 10. So let's look at some examples how you actually convert a number like this to a normal number, meaning how would you convert a hash from this representation to this. So let's take a look. Let's look at a simple example. Let's think about number 115, guys. So 115 in base 10. What does it actually mean? Well, it means that we take the last digit here and we take that times 10 raised to the power of 0. So why do we take 10? Because the base is 10. So we take the 5 here and we multiply it with 10 because we are operating in base 10. And because it's the last number, we use a raised to 0. And then we take plus 1, which is this one, times 10 raised to the power of 1. And then we take the last number, which is 1, times 10 raised to the power of 2. So you can see a pattern here, guys. We start from the end and we take the last number times 10 raised to the 0, and then we go one step, we take the next number, which is 1, and we take it times 10 raised to 1, and then the same thing for the third number, but now we multiply it with 10 raised to 2. And so if we would have more numbers here, we would take them times 10 raised to 3, and the next number times 10 raised to 4, and so on. And when we add these numbers together, we get 115. So how would we write 115 in base 16? Because this is base 10. How would we actually write the same number in base 16? Well, 73 is actually equals to 115. Let's take a look at why. So 73 in the base 16 means that we take 3 times 16 raised to the power of 0, like we did up here with 5 raised to the 10 to the power of 0. But now we have base 16, and therefore we take the last digit, which is 3, times 16 raised to the power of 0. And then we take plus 7 raised to the power of 16. And then we take plus 7 times 16 raised to the power of 1. And we'll get 115, because this is 3 and this is 112. And if we add 3 and 112, we'll get 115. So actually 73 in base 16 is equals 115 in base 10. Right, so now we understand how we actually use different bases and what different bases mean. So just to recap, guys, here we take times 10 raised to the power of 0 first, and times 10 raised to the power of 1, and times 10 raised to the power of 2. And so with each digit, when we go back from the last digit, we increase the power by 1, like this. And we just do the same here, but now the base is 16. So we take 16 to the power of 0 first, and then 16 to the power of 1. And then we just insert these numbers starting from the behind, like this. And so when we use hexadecimals, when we use base 16, one way to represent it is to write 7316 equals 11510, meaning that 73 in base 16 is equals 115 in base 10. However, in order to avoid these subscripts, which can be tough to write for, like, if you're using a computer and you want to write a subscript, that can be challenging. So instead of that, we just write 0x73 equals 115. So whenever a number starts with 0x, we know that this is in base 16. And so 73 in base 16, because it starts with 0x, equals 115. Right. So you might ask another question, meaning, namely, where do letters come from? I understand that we have numbers, but where do letters come from? So it comes to the digits. So in base 10, we have 10 different digits. And digits can hold a value from 0 to 9. However, in base 16, we need 16 different digits. And so each digit needs to be able to hold a value from 0 to 16, or to 15. So from 0 to 15. And therefore we have the normal digits 1, 2, 3, 4, 5, 6, 7, 8, 9. But we also have some extra digits. And because we need a way to express them, we use letters. And so A, B, C, D, E, and F are extra digits in base 16. So A means 10, B means 11, C means 12, D means 13, E means 14, and F means 15. And so each digit in hexadecimal notation can hold a value from 0 to 15, as we can see here. It can be a 4, that would be a regular 4, or it can be a D, and a D would be 13, because E is 14 and F is 15, guys. Right. So let's look at some examples. As we mentioned before, A is equals to 10. So when we write like this, it is equals 10 times 16 to the power of 0, which is only 10. And we just ignore the 0x because it just tells us that A is a digit in hexadecimal notation. So we can just ignore this 0x and just look at A. And so next we have AB. Once again, we ignore the 0x because it doesn't mean anything. And we just look at A and B. And as before, we start from the end. And so we take B, which is 11. And therefore we take 11 times 16 to the power of 0 plus 10, which is A, times 16 to the power of 1. And we get 171. So A is equal to 10 in base 10, and AB in base 16 is equals to 171 in base 10. Let's take a longer example. What is EF6? Well, we start from the end. 6 is 6 times 16 to the power of 0 plus 16 times 16 to the power of 1. Why do we have 16? Because F is... or actually this is wrong. This should be this should be 15. So this is 15 and this is 14. So 15 times 16 to the power of 1, and then 14. So let's just imagine that this is 14 times 16 to the power of 2, and we'll get this answer. And this has to be correct because I didn't calculate this by hand beforehand. So, and then we get this number in base 10. So this number in base 16 is actually equals this number in base 10. So as you can see, guys, we have now translated several numbers from base 16 to base 10. And so, and a hash that looks like this is just a regular number. However, it is written in hexadecimal notation. So in order to get this number from this, we would take 2 times 16 to the power of 0 plus 3 times 16 to the power of 1 plus 15 times 16 to the power of 2 plus, so C is... So A is 10, B is 11, C is 12. So therefore we take plus 12 times 16 to the power of 0, 1, 2, 3. And lastly we'll take D, which is 13 times 16 to the power of 0, 1, 2, 3, 4. And if we just add everything together, we'll get this number. So that's it, guys. That's how you convert a hash to a number. And now you actually know that each hash is just a normal number and it can easily be compared to any number. This is super fast to do for a computer. This is the typical task a computer is very good at. So that was it for today, guys. What do you think? Did you know how to do this operation beforehand? Leave your comments in the comment section below. And if you are a new viewer, guys, and you like blockchain, you like Ethereum, Bitcoin, you like technology as a whole, you should definitely subscribe, guys, because you will find this channel interesting. I myself am a software developer and I post videos every single day, guys. Also, guys, I've started posting on Steemit. I'll link my Steemit account in the description. So go ahead and check it out if you like. And I'll see you guys tomorrow.